Hey folks, Brian Keene with OCCAM Defense, and today I'm going to talk about astigmatism, red dots, peep sights, and all that. Part one here is the problem. In part two, we'll talk about the solution. Going to try and keep this short and sweet for you with a minimum, actually no formulae, and we're going to keep this real nice and simple. And I'm going to tell you stuff where you're going to know 90% of it just from walking around and paying attention. First, we'll talk about the many ugly faces of astigmatism with respect to red dots. If you are young and or older with really good eyes, your red dot probably looks like this picture at left, actual dot. Nice, small, well-behaved circle. And if that's your reality, you can kind of forget about the rest of this until you're older. But I would urge you to follow along because this will change the lives of shooters in your life. And it's such a gift to be able to share this with people because it really will take them from having been a good shooter and now they just can't shoot. They think they can't do it anymore, to back in the fight and really shooting well. This is my situation. I absolutely need the solution that we talk about in part two. And with that solution, I'm able to shoot well under 1 MOA. Which you wouldn't think you'd be able to do, but you can with a red dot. Okay, let's get into the puddle of spilt sorrow, as I'm euphemistically phrasing it here. The most common effect would be just that you see a really big dot. Now, like in my case, that's kind of my deal, and I see a dot that's almost exactly 4 MOA when I'm shooting, and that's a bummer. You cannot shoot, and I cannot shoot sub 4 MOA uncorrected. Or shoot sub MOA with a 4 MOA dot. Case number two, you could see kind of an infinity symbol or an hourglass shape. You could also see a slash that could be going any direction. You could see kind of a halo around your dot, or you could see some gnarly combination of all of these things with like sharp little dots that don't have much to do with anything. Okay, so now we know what our enemy is. Let's figure out why it's happening. I've brought up the list of refractive indices here. Wikipedia has a pretty decent treatment of this, but it's on YouTube. I don't need you to know everything that's on this page. I'm just telling you this is the root physics that we're working at, that when light goes from one medium to another that has a different refractive index, it bends. And if you want to learn more about it, this is a pretty good place to start. This is what you already knew, is that when you're a little kid with a stick trying to stab a goldfish in the neighborhood pond, you missed. And the deal is that if you want to hit a fish with a spear, you need to aim underneath it. And this is one of the things that I can almost guarantee that you already knew. What's going on there physically is that light particles from the sun, we're not going to talk about wave particle duality, we're just going to treat think of it like rain. It's just you got a little particle, and that's a sun particle, and it's moving in a more or less a straight line from the sun to the earth, goes through our atmosphere, goes through the water, and hits a fish scale, and then is re-emitted along, in this case, this path, and then it bends when it leaves the water, and it hits your eye. Because we interact in in air most of the time, it's really non-intuitive for us to think that that thing right there is actually down there. But that is actually the reality. So you need to correct for that. And of course, the deeper the fish is, the worse this effect gets. So it takes a lot of skill to bowfish or spearfish from outside the water. You guys who can do it, props. I've tried. I stink. Here is the first part of your eye where this refractive index thing comes into play. It's the basis for lenses. And of course, you can use a mirror as a lens. We're not dealing with that here, although it will be a factor with how the red dot works. There's some diagrams I'm about to show you, and they confused the heck out of me when I was a kid in physics class. They use arrows, and the thing that I want you to keep in mind is that when you see a line like this black one here moving, that we're charting the potential path of one photon emitted from one very specific location. And that photon could come in this angle, it could come in this angle, it could come even further down, But the case that we're working with here is that it hits at this place in your eye and it's bent a couple times by those refractive indices I was telling you about. And it travels through the liquid that's in the middle of your eye, and it hits the image sensor on the back, which we call the retina, and it's inverted. And that is, we actually see upside down. We're not going to talk about it any more than that. Really, lots of places you can find on YouTube. Very much encourage you to go study that. The last thing you'll need to know in terms of like basic physics of schematically what's going on is that with a red dot sight, there's a little LED, light emitting diode, down in this corner here that emits light in a very narrow cone, which hits the inside of the lens, forward lens in the red dot. And that's why your red dots appear broken when they show up. The lens is at an angle. That's to facilitate this bounce, and there's distortion that happens from that. A bunch of companies will actually grind the lens in special ways to minimize that effect. But keep thinking in your mind, just keep tallying up the imperfections as we go along here, because there's very little that's perfect about real life. Here's a better drawing of that cone angle. And so you're going to get light coming in from different areas on the lens and at different angles. Okay, this is a sort of a classic, the first thing you see in physics optics class. No equations, we're just going to talk about 3 cases where light can be coming into your eye. So for right now, imagine that this is that candle flame. Down here is your image sensor, your retina. These are the focal points. We'll go over them very briefly. And then think of this as the stack up of your cornea and your lens. The simplest case in red here is that light comes in parallel to the long axis, to this dotted line down here. Comes in parallel, and parallel light coming in and with a perfect lens will always go through the focal point. That's why it's called the focal point. It's going to keep on going and hit the back wall of your eye, and we talked about that inversion. Again, these arrows will really confuse you if you don't remember what they are. It's really just a vector, if you remember that. It's not the image. We're pointing at the one little, think of it like a pixel, this one little place in space where light can be emitted from. If you wanted to properly image this arrow, you'd have to do this exercise, 1,000 times from the top to the bottom, and then you could chart how the arrow would actually look on your optic nerve. So the first case, light's coming in parallel here. It gets refracted by the lens, and it hits this point. The second case, which is interesting, goes perfectly through the center, winds up in the same location. The third case is the reverse. The blue is the reverse case of red. These are reversible processes. They're symmetric here. So we said we came in parallel and went out through the focal point. The last interesting case is where you go in through the focal point and wind up parallel. And everything's tied up in a nice pretty bow. All of the light, no matter where it hits the lens, is going to end up in the same location. This is the case when you do not have astigmatism, or at least not everybody's got a little. Nothing's perfect, but if you can't perceive it, this is more or less your situation. Let's look at what an old eye looks like. It's lumpy, and it might look like a football. You might have a scar somewhere. Some of this is surgically correctable. We're not going to talk about that. We're just going to talk about the lumps. So same as before with the red track. Same exact deal. Same with the black. But when the blue one hits this lump, the incident angle, and I mentioned it, or I went over it very briefly with the Wikipedia article, but the angle you come in determines the bend. And in this case, because this thing isn't smooth anymore, it's putting English on that light particle, and it did not hit the target. It's like a bullet hitting a sapling or something and kicking off into left field. This is a problem. This is what the root cause of astigmatism is, this right here. How do we fix it? Luckily, there's a really easy way. Pinhole camera is kind of the punchline, which is also what a Peep sight is. And we're going to deal with that in part 2 of this video. I'm going to attempt to stick that up in the corner of your screen right now. If not, please follow along at OCCAM Defense and Instagram OCCAM Defense Solutions. Thanks very much for watching. Talk to you soon.